We look at net area. It's the same thing as the Riemann sums, but just now we were looking at everything above the x-axis, right? And we saw everything from the curve down to the x-axis. Everything gave us a positive area, right? So our net areas is now gonna say everything above is positive, everything below is negative, so we can have some canceling out from the top and the bottom. So when we look at the Riemann sum, know a general formula for that. For the midpoint one, if we choose, f of x, let's say k star, times your change in x, and your change in x is equal to b minus a over n, right? So if I have a picture that falls below the x-axis from A to B, say something like this. Everything above has positive contributions, everything below has negative contributions. All right, so definition, the net area is the sum of the areas of, of parts above the x-axis minus the sum of the areas of the parts below the x-axis. All right, net area can be positive, negative, or zero. All right, so evaluating definite integrals. Theorem says if f is continuous on a to b, closed interval, or bounded on that interval, with a finite number of discontinuities, then f is integrable on a to b. Much easier to see this interpreted with a picture. All right, so from A to B, okay, so we do have some discontinuities, right? You can see as I have to lift my pencil up to be able to continue the function. So really I ought to put the function, let's draw it in red, like this. And then it's open here, from here to here. Open there. So the vertical lines right here are not part of the function. And so that's my function. So this function is discontinuous, but if I go all the way up to the x-axis at those points, I'm creating regions. I can still integrate this function. So region 1, region 2, region 3. To integrate this, it's really taking a Riemann sum of each partition there, right? Region 1, region 2, region 3, and add them all up, and you'll see region 2 is going to give us negative area. But all I'm doing is the net area is equal to the integral sign. Remember we did the indefinite integrals before, where we just did antiderivatives? And now this says definite integrals is from A to B. So you start at the bottom A and you put B there. You put your limits, your bounds right there of the function f of x dx, which is the area of regions 1 and 3. Minus the area of region 2, right? Notice this picture right there, that integral sign is a really long S, right? That's summation. That's the shorthand way of saying summation. That's the summation of f of x dx, okay? F of x, we just did that, Riemann sum, right? F of x, k star, k minus 1, whatever, times dx. change in x. That's all it is. This is the Riemann sum. Okay, but before we actually go into the antiderivatives and then using the fundamental theorem of calculus and all that, we're going to still work with this using Riemann sums and just a little bit of geometry for the first part. So look at this real quick. If I have an integral from 1 to 6 of 2x minus 6 dx. Now, if you've taken calculus, you know what the answer is quickly, probably, to do this. Same way we just did the indefinite integrals, took the antiderivative, blah, 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 blah. But using geometry. The net area is equal to what? Well, 2x minus 6. That's just a nice function, linear function, very simple. We can draw that. That is a y-intercept of -6 with a slope of 2, rise 2, run 1, right? I have a graph that looks like that. And you can plug in the order pairs if you want. At these bounds, we're going from 1 to 6. At x equals 1, you can see 2 minus 6 was -4. That's that point right there, right? So we're looking at that area below the x-axis. All the way to now we're above the x-axis. That's 1, 2, 3. 3 is actually the x-intercept. Of course, I'm not. If I had some nice graph paper, I could draw this a lot better. 2, 3, 4, 6. Putting in 6 in there makes 6 up here, right? 2 times 6 is 12 minus 6. We draw it there, 1 and 6. So we're looking at areas of triangles, right, for this particular shape here. An area of a triangle. 1/2 base times height, right? So we're going to look at the area region 2 minus the area region 1. Region 2, 1/2 of the base, 1, 2, 3, 3 units, times the height went up to 6, right? So that gives us 9, right? Region 1, again, 1/2 of the base, you can count it, physically count it, 1, 2. Of the height of that triangle, well, it's not really height, it's kind of like going down, but that is 4 units down, right? So that's 4. So 1/2 of 8 is 4. So the area, net area is 9 minus 4, which is equal to 5. All right, so net area is totally different than total area, because net means above the x-axis positive, below is negative, right? It'll have negative contributions. It'll take away out of your positive contributions already. So whenever you're actually doing actual real physical applications or something, you might be asked, what is the total area that's involved? So you're gonna have to compensate for this. Okay, so you're gonna have to figure out where is the graph below the x-axis. And so that is gonna be added back into the positive contributions to the parts that are above the x-axis. All right, let's do one more like that using geometry. Find the net area. Now, of course, all these geometric shapes are going to be circles, triangles, rectangles, those kinds of things that are easy to compute. So if I have the integral between x goes from 3 to 4 of a square root of 1 minus x minus 3 all squared dx. I'm like, oh, in the world is that? This is actually my guess. Take off the square root and equals to something squared. No. If I take out the square root, you got a circle. Right? Square root it, now we're looking at the top half of the circle. So we're looking at a semicircle between 2 and 4, actually. Radius of 1. Radius of 2. Yeah, radius of 1, diameter of 2. And you can put that in the calculator if you need to. Put the square root, just y equals that, and see what the graph looks like. And you'll see it, this portion here. And we're concerned about from 3 to 4. I just want that. Well, isn't that a quarter of a circle? Full circle area is what? Pi r squared. That's a quarter of the circle. So 1/4 of the radius, 1 pi, which is squared. So this is just pi over 4. So again, if you needed to see this, this is equal to a function, let's call it y. Y is equal to the square root of 1 minus all this squared. Square both sides. Move this to over there, you got x minus 3 all squared plus y squared is equal to 1. A circle with radius of 1 with its center at 3, 0. All right, let's look at in terms of a Riemann sum. If I take the limit as a change goes to 0 of my summation, k goes from 1 to n of, let's say, 3 times x sub k star squared plus 2 times x sub k star plus 1 times a change in x sub k. You can see what the function is, right? The original function was anytime you have, we were just doing x of k star, right? We plug in whatever that may be into the original function. In this case, x is being squared multiplied to 3, x to the first power multiplied to 2. This is just a quadratic right here, right? So it's a quadratic function right there, and times you change in x right here. So this is the limit of a Riemann sum for a function on an interval, let's call it a to b. So let's say if I choose, let's say if a is equal to 1, b is equal to 3, we can rewrite this as same thing we have written there. Really don't, probably didn't need to rewrite it, but that's all right. 3 times x sub k star plus 2 times x sub k star plus 1, change in x sub k, is equal to the definite integral now from 1 to 3 of the function. We just said, what was the function? 3x, I forgot to square it there. 3x squared plus 2x plus 1. Change in x is also dx. You could use any variable you want. Most of the time, x is the typical variable, or if I want to say t, I can still go 1 to 3 of 3t squared plus 2t plus 1 dt. It doesn't matter what variable you're looking at, right? So I can go just the other way. If I give you a definite integral, we can rewrite it as a limit. So if I say from 0 to 2 of x cubed plus 1 dx, this is equal to the limit as n goes to infinity. How many partitions we have, how many rectangles, an infinite number of them, of the summation as k goes through 1 to n, totaling all those rectangles, of f of x of k star, we choose the midpoint, times delta x of k star, change in delta x of k, not k star. X of k star, we know is equal to starting point plus the change in delta from 2 minus 0 over n, k times that. So this is just 2k over n, right? Okay, equal 1, 2, all the way to n. So my Riemann sum is f of this k star times my change in x of k, which is 2 over n. Should do that. Change in x of k is b minus a over n, right? B was 2 minus 0 over n, 2 over n. F of this is the 2k over n cubed plus the 1 times the 2 over n. Now you plug all that in the calculator. But we're going from actually can't put it in the calculator. We got two variables in there, right? So let's use some properties of summations. I distribute it across. This is 2n times the 2k over n cubed plus the 2 over n Right, look right here. This would be 2 cubed over n cubed right here and there, and a k cubed, right? I'm going to skip a step. Times another 2 over n. So this is 2n all to the fourth right there, times a k cubed, plus a 2 over n. N is a very, very big number, right? It's going to infinity. K is fixed, right? K goes from 1, and then the 2, and then the 3, all the way up to n. So 2 over n to the fourth is some constant. We're going to see what that goes to in just a second. That should be times the summation of k cubed plus another summation of this constant two over n could come out of just 1 as k goes through 1 through n. Remember, summation of a constant is the constant times that number of times it goes through n, k times n. So we just put in that to be 1. This right here, there was a formula. I think I may have told you those. Some special formulas, you didn't really have to memorize them, but if you want to do them by hand, you can. Summation as 1 goes through n of k cubed takes on the formula of n squared times n plus 1 all squared all over 4. This is what we just said, 2 over n times how many? N of them. All right, clean all this up. You'll see a lot of things are going to cancel out. I'm not going to bore you with the algebra, just kind of just want to hit home, make a point a little bit. But you square this, multiply it to n. You'll have n to the fourth down here. You can divide those out, cancel this with this. And then these ends will cancel, multiply that 2 times this. And all this comes out to be by magic, okay? I don't feel like wasting all the time on the algebra. Gives you this. Okay. We're taking the limit as n goes to infinity. So our change is going to 0. So basically creating a lot of rectangles, right? So the change is insignificant between rectangles, right? They're so minute, those skinny rectangles, right? Of this 4 plus 1 plus 1 over n squared plus 2. Now, if you go to infinity, 1 divided by a huge number is what? Close to 0. 1 squared is 1. 4 plus 1 is 5. Actually, that's 4 times, not 4 plus, right? course, directly in front of parentheses. So 4 times 1 is 4, plus 2, this limit is 6. That's the same problem we just did earlier, right? Try to use a Riemann sum to estimate it using just 50 partitions. Now we use an infinite number of partitions, and we kind of made that conjecture that, hey, I bet it's 6, right? But that's the proof of it right there, okay? Changing it to a Riemann sum, okay? And then using your summation properties to simplify it all the way down. So this is the same thing as doing from 0 to 2 of x cubed plus 1 dx. That is equal to 6. That's your idea of a definite integral. Okay, so evaluating between bounds, okay, the net area. Now let's get to the easy stuff. .3, the fundamental theorem of calculus. Sounds important, right? Sounds like that's the whole thing.